Hi and hello everyone. Welcome to the online video lectures. My name is A. J. Prakash, Assistant Professor, Department of Electrical and Electronics Engineering, St. Martin's Engineering College, Secunderabad. Today's my topic is on power electronics, and coming to the specific subject, it is like three-phase inverters and single-phase inverters. Let us see what is three-phase and let us see what is single-phase inverters. Basically, what is an inverter? An inverter is a power electronic device which converts DC power into AC power. Or else, when there is a DC source and when we want to convert into an AC source, we have to use a power electronic equipment called power inverter. So, the basics, a block diagram, you can represent it as so this is DC and the output is here, you will get as a AC output. So this is what an inverter. It has various applications. In today's life, we have batteries, we have solar power, we have renewable energy sources. In all these sources, there is a requirement of inverter because all our loads are AC loads. Therefore, this is a very important topic to study and also useful for our day-to-day life. Let us see. So what is an inverter? As I told, is a power electronic device which is used to convert DC voltage to an AC voltage. It is a static device. There are no rotating parts. Therefore, it has very good efficiency. Then it converts from one part of the one form to another electrical power, that is DC power to AC power. Here it is a converter but not a generator. Please remember, it is a converter but not a generator. So we have a DC source and we have an inverter. Inverter has various power electronic devices and then it converts to AC power, which is alternating in nature. Then what are various important components of an inverter? So we have various components of an inverter. Those are semiconductor switches like IGBT, MOSFET, thyristor, and power diodes. And then we have voltage and current sensors. In order to find what is the type of voltage it is generating, what is the frequency it is generating, we need voltage sensors, and also based on the current, what is the amount of magnitude of the current we need to know. To know it, we need current sensors. And these sensors are used as a feedback to the inverter so that we can control both voltage and current. And then the third important one is DSP or any other controller, because as we are using switches, we need to generate signals for the switches to turn on and turn off. So those can be brought out, those can be generated using a controller. In the controller, we can write some mathematical equations, and we can also use some PI controllers. We can use other controllers to get the required voltage and required power output. And the fourth, as I told now, we need switching signals for the switches. These are generated by the PWM module. What is PWM module? It is a pulse width modulation module. This module will generate the required switches signals for the switches to turn on and turn off, so that the output voltage and output frequency of the voltage we can control using this PWM module. And then we have a PLL. PLL stands for phase lock loop. So this is majorly used in a grid integration inverters. So when we want to integrate inverter to a grid which is having already a AC voltage source, we need a PLL so that the phase sequence will be same. If not, there is a mismatch of phase sequence, there is a problem of short circuit. Therefore, we need a PL, phase lock loop circuit, to get the theta from the grid. And then we need to find what type of load we are connecting. Therefore, load is an important parameter of the inverter. And then we have filters. Filters are used to eliminate the harmonics which are generated by the inverter. So the purpose of the inverter is what I told. It is to generate an AC waveform, but sometimes a pure AC cannot be obtained using a static inverter. Therefore, we need to use filters to eliminate those harmonics. And then what are the requirements of good conductor? The good conductor always has a good output voltage, good frequency, and then it should have less electromagnetic interference, and then the size of the filter should be very small. Then what are the types of inverters? There are various types of inverters we are using regularly. There are different types of inverters, and these are classified broadly into 4 types. One is based on the waveform generated. Based on the waveform generated, it is square waveform, sinusoidal waveform, based on the type of the load, single phase inverter, three phase inverter, and based on the level of inverter, 3-level inverter, 5-level inverter, 9-level inverter. So as you increase the number of levels, what happens? The pure sinusoidal waveform will be obtained. Therefore, that is the purpose of increasing the levels of the inverter. And then we have PWM techniques. Based on the PWM techniques also, it is it is classified as SPWM and SPPWM technique, and based on the topology, cascaded HBC topology, diode clamped H topology, and capacitor clamped topology. These are the major classification of types of inverters. And then let us come to single phase inverters. Single phase inverters are two types. One is half bridge inverter, the other one is full bridge inverter. Then coming to half bridge inverters, let us see a circuit model of a single phase half bridge inverter. So this is a single phase half bridge inverter which has two thyristors and two diodes. Diodes are used to when you have a RLE load, when you want to inject power into the source, then there is some like back EMF E. So such kind of loads we need diodes D1 and D2. Therefore, these are always used to improve the power factor of the inverter. So this is the type of the method of connection, and load is connected between terminals A and B, Vs by 2 and Vs by 2. And then let us see how a single phase bridge is operated. It has two modes of operation. One is, because in AC we should get positive half cycle and negative half cycle. Therefore, we should have two types of modes. One is mode 1. Mode 1 is what? When such switch T1 is turned on, what happens? The current flows from T1 to and then load to this. And when mode 2 means what? Is when T2 is turned on. Therefore, again the current flows in the reverse direction. Therefore, in this case, in mode 1, B is positive and A is negative because it is connected by via T1. Whereas in mode 2, whereas in mode 2, B is connected to the next. P is connected to the positive of the Vs by 2, whereas A is connected to the negative of the Vs by 2. Like this, we can get the alternate voltage sources by switching T1 and T2 instantaneously by giving some gap so that the switches can be turned on based on this. And then let us see the waveform. This is the waveform of the half bridge inverter, where you see Ig1 is what? At this point, the switch T1 is turned on. Therefore, we have given Ig1 as some magnitude. And after T1 is turned off, then Ig2 is given. Therefore, this T2 is turned on. So what happens during T1 is turned on? As I told, B is positive and A is negative. Whereas when T2 is turned off, A is positive and B is negative. Like this, we get an alternate voltage source. Now you can tell, by seeing this figure, that this is an alternating square wave. Okay, this is not a pure sinusoidal. So this is the way where an inverter used to get from DC. So we can generate the DC power, we can convert the DC power into an AC power by alternating switching the thyristors. Okay, this is the, now let us go for the what is single phase full bridge inverter. What is the circuit model? This is the circuit model of a single phase full bridge inverter, where we have used 4 switches T1, T2, T3, T4, and then 4 diodes. As I told earlier, diodes are used only when you have an RLE load, or when there is a load when load is a source also. When load is an access source also, then diodes are used to improve the power factor of the power electronic circuit. Therefore, we have 4 switches here. Let us see, it has 2 different kinds of modes. To get positive half cycle, we need to turn on 2 switches, and similarly to get negative half cycle, we have to turn on 2 more switches. Let us see the mode 1 and mode 2 operation. As I told here, in this diagram, T1 and T2 are turned on. Therefore, current flows from A to B, and the switching signals are given as Ig1 and Ig2. Okay, and let us take T is the total time period of the waveform. Then half of the time period, Ig1 and Ig2 are given. Therefore, T1 and T2 are turned on. Similarly, coming to the below diagram, what happens? You got a positive cycle. Now what I do is, you turn on T3 and T4 by giving gate signals to the switches. So what happens now? The current direction will flow from B to A, and therefore you get a negative half cycle of the output voltage. So like this, you can get a positive half cycle by switching T1 and T2, and you can get the negative half cycle by switching T3 and T4. Okay, a alternating voltage output can be obtained, and this voltage can be connected to the required load. So based on the load, the current waveform will be modified. If it's the R load, then the current waveform and the voltage waveform will be similar. If it is a RL load, the inductor current will slowly lag behind the voltage, as we know that inductor current always lags behind the voltage, the current will be lagging and the behind the voltage, therefore it will be not a pure square waveform. Okay, as I told, this is the pictorial diagram. You can see here Ig1 and Ig2 are turned on at the half of the time period, and next half of the time period Ig3 and Ig4 turned on. Here we get a positive half cycle. As I mentioned here, T1 and T2 are turned on, and you get a negative half cycle, T3 and T4 are turned on. Therefore, what is the current equation? If it's R load, as I told, if you get a R load, the R load is symmetry is equal to the shape of the R load is current of R load is similar to the shape of the voltage waveform. Okay, then what is the frequency? The frequency here is what? 1 by time period hedges. So this, now you can tell me that the time period, the output waveform frequency or output voltage waveform frequency is depends on the time period of the switching time period. It depends on what? Switching time period. You can increase or decrease in the switching time period based on your application. Okay, then what are the performance parameters of inverter? The performance parameters of inverter means how to calculate or how to justify whether the inverter is a good inverter or a bad inverter, and what are the various ratings of the inverter. Means what is its voltage, what is its frequency, and then what is the power rating. Power rating is very much important, which is mentioned in kilowatts or kVA. And then what is the efficiency? So efficiency, we know that it's the ratio of output power by input power. Okay, so if the ratio is very high, then the inverter is very good. That means, but the DC power which is given is maximum of DC power is converted to AC power. Therefore, the efficiency of the inverter is high. And then power factor. Power factor is what? Real power by apparent power. We also know that power factor is one of the important parameter of inverter, because when we connect different, when we are having a switching loads here. So switching loads means after certain period of time we are switching on and we are switching it off. Therefore, the current waveform of the inverter is not similar to the voltage waveform. Therefore, the power factor will be coming. The topic of power factor will come into picture. Therefore, we need to see the what is the power factor of the inverter also, and then switching frequency. So, based on the required load application, we can increase or decrease the switching frequency. In general, what we use is IGBT and MOSFET. MOSFET is used for high switching frequency, whereas IGBT switches are used for low switching frequency, and whereas thyristors are used for very low switching frequency. Majorly, the thyristors are used for HVDC, high voltage DC transmission applications, because the output waveform is around 50 hertz. And then single phase inverters. What are the applications of single phase inverters? We know that single phase inverters are used in uninterrupted power supplies, UPS, in a daily offices, in households applications. When there is a power cut from the source, we use batteries. So, and these batteries will convert from DC to AC. And then renewable energy sources. As we know that we are moving towards the solar PV power, solar power. Therefore, solar power is a solar PV array is a DC voltage source. So, we want to convert the DC voltage obtained from the PV to the grid. Therefore, we need an inverter to convert the DC power into an AC power. And then we have electrical vehicles. So these are the upcoming technology. And in India, the electrical vehicles are increasing day by day. So what does the electrical vehicle have? Again, an electrical vehicle has a battery. So when we have a battery, definitely we need an inverter or other powertrain converters also to convert the DC power into AC power. And then we have portable emergency power systems like hospitals, etc., where power is very needed, where a backup is needed. These plays much role using power electronic converters. We can convert the DC power, which is stored power, into an AC power, which is very much required. Then what are the disadvantages of single phase inverters? I am talking about single phase inverters, as these are low power output, means we cannot use for higher power applications, and then they have poor efficiency as increase the loads. Okay, therefore we cannot get that much amount of output from this. And then we have some slight of voltage fluctuations, because we cannot use a high level PWM technique in a single phase inverter, and therefore the voltage waveform is not much sinusoidal. Therefore, we get some voltage fluctuations. And then high ripple current. What is ripple? Ripple means what? Peak value by the instantaneous value. Therefore, the peak value will be higher. Peak value by average value. The peak value will be always higher than average value. So this will be larger than the single phase inverters. And when you apply such kind of inverters to motors, the torque is not constant. Therefore, there is a lot of noise in the induction motors when you use such kind of single phase inverters. And then harmonics. What are harmonics? As I told you, harmonics are generated because of inverter. Because inverter is not pure sinusoidal waveform, therefore harmonics are used. Harmonics are obtained. So what are the types of harmonics? The definition of harmonics is what? It is the integer multiples of fundamental frequency, and then therefore you have third harmonic, fifth harmonic components. We call odd harmonics. Odd harmonic means it is a third component, fifth component, and seventh component. Means see, you can see the shape. See, this is one type of harmonic. The blue one is what? 50 hertz component, where we have other components which are of other frequencies, that is third harmonic frequency, which has a frequency of 3 into 50, 150 hertz. And then fifth harmonic, we have a frequency of 5 into 51, 250 hertz harmonics. So these are generated in the power electronic converters, especially inverters. These are very which have very negative effect on the performance of the inverters. Therefore, these should be reduced. What the effect, that is what effects of harmonics. So the effects of harmonics are what? It introduces power quality issues. If you use in induction motor, other machines, this inverter, it can increase the overheating of the machine, and then the efficiency of the inverter will be reduced because of these harmonics, and then additional power loss are introduced because of these harmonics, and high frequency. And when you are using for a sensitive load, because sensitive loads are to be controlled very precisely, because of the introduction of these harmonics, the control variables will be get disturbed, and we cannot control the output voltage or current of the inverter because of these harmonics. So equipment like what generally the equipment PLC systems, medical devices, and communication systems may get malfunction because of these harmonics. So hence the harmonics are always to be reduced by using filters or using some different kinds of PWM techniques, etc. Let us see the next slide. See PWM techniques. Especially the purpose of PWM techniques are used to get the switching signals which are to turn on and turn off the inverter. Okay, there are different kind of PWM techniques. Okay, generally for this level we can go for a single pulse width modulation technique or sinusoidal pulse width modulation technique. These are very much basic things. Okay, so I have also mentioned here single pulse width modulation technique. So these are used to turn and turn off these semiconductor devices. And then we have sinusoidal pulse width modulation technique. So when you use SPWM technique, the output voltage will be similar to the sinusoidal, but not a pure sinusoidal. So that's why you have to increase the switching frequency, or else you have to use other additional PWM techniques to get the pure sinusoidal waveform. And then THD, total harmonic of PWM technique, a PWM technique that offers better DC supply voltage consumption than sinusoidal PWM. Then carrier based PWM. Okay, carrier based PWM is based on the carrier signals. So we have one topic called carrier based on carrier signals. We can change, we can get different type of PWM signals. We can modify the pulse width modulation of the signals. Therefore, we can get the average value near to the sinusoidal. So that depends on the carrier waveform. Such kind of a PWM technique is called carrier-based PWM technique. And this is third harmonic PWM technique. So what is third harmonic? We can inject third harmonic into the PWM signal so that it is eliminated from the output. That technique is called third harmonic PWM technique. And then we have selective harmonic elimination. If there is some device and some device, that device will be resonance to that frequency, we can reduce that frequency component by using this technique, that is called selective harmonic technique. For example, there is a device which is resonance to the fifth harmonic, or 5 into 250 hertz, it has a resonance frequency. Now I want to remove, if you want to remove the 250 component, you can use the selective harmonics technique to remove that fifth harmonic component from the output of the PV inverter. So based on different kinds of techniques, based on different types of applications, you have different PWM techniques. Only you have to choose the right one to the right load. And then you can see one example of a pictorial example of what is how PWM switches are generated, PWM signals are generated. For example, here you have a carrier signal, triangle is a carrier signal, and our reference signal DC signal. So whenever this DC signal is higher than the carrier signal, this part you got a pulse. Similarly here also, this part you got a pulse. Like this we can get pulses by comparing these two signals. Okay. Similarly, in this signal you have your reference wave is sinusoidal. Reference wave is sinusoidal, whereas the carrier is a sawtooth waveform. So by comparing the sawtooth waveform and the carrier waveform, you can get the pulses which are shown like this. These are called modulated pulses. Remember, observe that the pulses are not constant here. The pulse width is modifying, because this is that's why it is called as pulse width modulation technique. As I told, the pulse width modulation, because here we can observe that the width of the pulses are not constant. That's why it is called as pulse width modulation technique. If you observe these two signals, what happens here is a fixed pulse width is obtained in this type of a PWM technique. Whereas if you go for a sinusoidal PWM technique, you have a different pulse width modulation, pulses, width of the pulses. Therefore, the average value will be varied, and the average of, if you calculate the average value will be near to the sinusoidal. Similarly, you can increase or decrease the width of the pulses by changing the carrier frequency or reference frequency uh, output, reference frequency signals. Therefore, the PWM pulse width is generated perfectly to get the sinusoidal output. Now, let us come to three-phase inverters. Let us see the how three-phase inverters will work and what is pictorial, what is the power electronic circuit diagram. So, three-phase inverters are majorly used for high power applications, and moreover, we know that we have all three-phase power systems only. Therefore, such kind of power electronic converters will play a major role in connecting the DC sources to the grid. So, here we have a generalized three-phase power electronic circuit inverter which convert DC power into AC power. If you observe this one, you have three waveforms output here. We have six thyristors which are numbered as T1, T2, T3, T4, T5, and T6. You can observe these. The top switches are odd order numbered, whereas the bottom switches are even numbered switches. And the switches numbering is not a uniform as we write. The switches are numbered according to the switching sequence. So remember that the switches are numbered according to the switching sequence. Let us see how it is operated in the further slide. Okay. See here we have three phases. We know that what we turn that the phase of the three phases of a AC signal is what R, Y, B, which are mentioned here R, Y, B, and we have a neutral point because it is star connected, and then this is the DC voltage source. Okay, and these are three leg switches because we have different type of inverters. So this is a three leg switches. Okay, each leg is connected to one phase. See, you can see T1 and T4, this is one leg and it's connected to R phase. Similar T3 and T6 is one leg which is connected to B phase, and T5 and T2 are one leg which is connected to Y phase. Okay, RYB is a three-phase system. Okay, when T1 is turned on, then you see that when T1 is turned on, T4 should be automatically get turned off. You should do that because if not, the supplies get short circuited. Similarly, when T3 is on, your T6 should be turned off. And similarly, when T5 is on, you see that T2 should be turned off so that therefore the short circuit doesn't happen, and you have to do that because if not there is a dead short circuit and a large amount of current flows within the power electronic circuit. And I told that this is used for very high applications because it can generate a three-phase power which can be connected to the grid. Okay, now basic two types of techniques are there two types of methods are there to operate these three-phase inverter of a three leg. One is 120 degrees mode of operation, the other one is 180 mode of operation. So we can see the 120 degrees mode of operation. So 120 degree mode of operation in the sense the switches are turned on. That turned on time is 120 degrees. That's why it is called as 120 degrees mode of operation. If the switches are turned on for 180 degrees, in the sense you have a one full cycle is what 360 degrees. One full cycle is what 360 degrees. If you turn on the switch for 120 degrees, you can see here it is nothing but 120 degree mode of operation. Similarly, T4 is turned on for one more to 120 degrees, therefore it is a 120 degrees operation. So you can see that this is the method of operation. You can see that there are six modes of operation of a inverter, that is mode 1, mode 2, mode 3, mode 4, mode 5 and mode 6. Each mode has a conduction time of 60 degrees. That's why it is called as a 120 degrees mode of conduction. Similarly, you have one more mode of operation that is called 180 degree mode of operation. In that, the switches are conducted into 180 degrees. The difference is that the basic thing is that in 180 degrees mode of the disadvantage in the 180 mode of operation is that there is no turn off time. There is very little bit of turn off time is available for the switches to turn on, whereas in 100 degrees mode of operation you have 50 degrees of time is elapsed is present to turn off the switches so that it avoids a dead short circuit. Now what is the name? Now let us see how we can how the switches are turn on and turn off, and then how an three-phase A signal is generated using this 120 mode of operation. Moreover, I want to add one more point is that this is a very basic level of inverter. You have very different kinds of level inverter such as a 5-level inverter, cascade bridge inverter, and then we have diode clamp inverter, capacitor clamp inverter. In that inverters we have in that inverters we have more number of switches, but whereas this has only 6 number of switches. But this is very used for only low level of very low level of applications, but diode clamped and other kind of multi-level inverters are used for higher clamped inverters. Now let us I'll explain you with the help of a thing that so that you can understand very clearly. From this we can see that I'm going to explain you how the 120 motor operation is operated to get the AC output voltage. You can see here there is a conduction sequence. As I told now, the switches are numbered according to the conduction sequence. Therefore, the conduction sequence is 1 2 here. It is 2 3 for the next 60 degrees. It is 2 3, and then for the next conduction period, the switching sequence is 3 4, and then the next conduction period, the switching sequence is 4 5, and then you can see that 3 is turned off and 4 is turned off, 5 is turned on, and then 60 degrees we have 5 and 6 switches are turned on, and then for the next 60 degrees we have switches 6 1 and turned on, and those two are conducting in that period. So the total conduction time is, you can see the total conduction is 360 degrees here. Okay, you can observe that when switch 1 is off, 2 and 3 will be turned on. 2 is continued for 2 parts, that is 60 plus 60, it is 120 degrees. Similarly, 3 is continued for 160 plus 60, 120 degrees, and 4 is connected for 2 sections, it is 120 degrees, and whereas 5 is connected for 2 sections, it is 120 degrees, and 6 is connected for 2 degrees, 60 degrees. Now to get the operation, now let us see how 61 is operated. From that we can get the output equation for a current by seeing that by taking this 61, and then I am going to explain the method of how switch 6 and 1 is operated and how supply is connected to this system. You can see here the Vs is connected to the anode of T1 and anode of T3 and anode of T5. When, as I tell, when 1 is turned on, the current flows from positive half cycle from positive to the T1 and then comes back to A terminal, and then it goes back to the neutral point, and then goes back to T6 and goes back to the negative of the sources. That is why now you can see that a continuation of current is obtained and a closed loop is formed. So what I told, how current flows when a closed loop from positive polarity to negative polarity, you get a current. Current is flowing from now T1 to A terminal, and then it enters to neutral, and then it enters to B, and then it goes from B to T6, and then it goes to negative terminal of the source. Therefore, a continuous path is formed. So like this, you can operate the inverter in 120 mode of operation. Similarly, for other switches also, you can get this type of current flow, and then I can get this type of current flow, so that you can get a good equation. From this is what is A plate is positive plate and B plate is negative plate in conduction of, in this mode of operation. A is positive plate and B is negative plate, and then see equivalent circuit. So to get the current, we need a equivalent circuit of 6 1 conducting. As I told, no, switch when T1 is turned on, the A is connected to the positive polarity, whereas B is connected to the negative polarity. And then what happens? Now this is the equivalent circuit. Now you got a complete loop, and then the current flows from A to B, and then you have a neutral point in the middle. Now if you if you apply KVL for this to find current I, what happens? It is voltage by resistance. Okay, see the current loop, current I is nothing but voltage by resistance. Therefore, I is equal to Vs by R, and R in series. Therefore, it is I Vs by 2R, and then this is what the current flows, and then by this you can get the current, approximately current, so that the complete cycle is obtained. Similarly, you can get for different switches also. You can get current equation when other switches are operating, and from this you can find current waveforms. But remember that, as I told in the earlier, based on the type of load only, the current value will be changed. If the current value is not changed, if the current value is if the load changes, no, the current doesn't change. If the load changes, the shape of the current waveform is increases, and then we got Vn is equal to I into R, because this is the phase voltage, and if you take A to B, it is a line voltage. The Vn is equal to I into R, which is equal to Vs by 2. Similarly, what is Bn now? Bn is equal to minus Vs by 2, because it is connected to the negative terminal. Therefore, you can get the Vbn as minus Vs by 2, like this. Thank you for giving this opportunity.